Okay, so continuing with the formation of a hologram of a plane wave. Okay. So I have a plane signal wave, okay, plane signal wave of frequency omega. Then I have a photographic plate in the xy plane. This is the xy plane. So I start off with a two-dimensional thing, okay, and the wave is traveling along in the z direction, and the interference pattern or interference between these two waves will be formed on this xy plane. Okay. The reference wave is formed by dividing the wave front with the help of a prism. So I call this as the reference wave. Okay. So I have divided the wave front. So I ensure all the coherence part is ensured. Okay. And the angle of inclination of the reference wave to the z axis is theta. Okay, here I have shown theta. This is the z axis and this is the angle. And this is my signal wave. So this is my reference wave and this is my signal wave. So how do I describe the signal wave? Like any other wave which we have done so many times before, Es, S stands for the signal, and is equal to E1 e to the power minus I omega t minus kz. Okay. And E1 is the amplitude. And Er, which is the reference wave, that means this one, E1 it has an amplitude of E0. So this wave is E0 e to the power minus I omega t minus kzz minus kzx. Okay, this phase part you can obviously, this is the k along the z axis and the k along the x axis is involved. This is the x axis along the z axis and the x axis. Okay, and we are recording it on the xy plane. So it is traveling along z, so omega t minus this is the phase part, this whole part. So I need a component of k which is kz along the z axis and a component of k along the x axis which is kx. So E1 and E0 are real amplitude, and from here by geometry itself you can see kx is equal to k sin theta. Sin theta is opposite upon hypotenuse. So this opposite is k sin theta, and so kx is equal to k cos theta is almost equal to k. Okay. Or you can just write it as kx, whatever is your x, whichever point you want to record the image at. So kx becomes kx sin theta. Okay, here it is, I have written it here, this comes here. So the value along z axis is kz, because this k is going along this direction. Along this axis, it becomes kx sin theta. Okay. So the total electric field, as you know before, we have to take the sum of Es and Er. Okay. So e to the power I omega t minus kz, I just add up these two. Okay, add up these two and I take this out common outside the bracket. So I have E1 E0 e to the power I kx sin theta. The intensity distribution then, intensity distribution is E star E or mod E whole square, however you want to say it. So intensity distribution is E star E. So this is this E. So I take E star E of this whole part. So it turns out to be half E1 square E0 square plus 2 E0 E1 e to the power I kx sin theta. So the moment there is a e to the power I theta term, or you know it is a undulating intensity. Undulating intensity. Okay. Undulating intensity means it is an interference pattern. Okay. So it is an interference pattern like this, or okay. So this is the intensity which you will get on the xy plane. All right. So this is the intensifier. The photographic plate records this, and thus it records the phase difference between the reference wave and the signal wave. Okay. Now that part is very obvious to you. The moment there is an interference pattern, that means it has put in the information of the phase, okay, or the phase difference between, say, the signal wave and the reference wave. So, I have got an interference pattern on this plate now, but that is not the end of the story. We have to reconstruct this whole thing. Okay. We have to reconstruct the plane wave that was my original plane wave, which is here. Now, all this will be removed and I only have this holographic plate, or the hologram as it is called. Okay. Actually, the term hologram means the whole picture. It is from some Greek word. Anyway, so I just take out this plate and I must be able to read what is there on that plate. Okay. How do I read it? Okay. Oh, before that, I think you should again keep at the back of your mind a photographic emulsion, which we have seen in that second slide. A photographic emulsion consists of silver halide particles suspended in a gelatin base. This emulsion is applied to a glass surface. Okay. So, glass surface, so it will be partly transparent and partly reflecting. When the light falls on a silver halide particle, so it is made of that silver halide particle, it creates centers of reduced silver or development centers. Particles containing development centers are reduced to a metallic silver. Okay. It was silver halide first, and then when light falls on it, it becomes metallic silver. If there are no development centers in a particle, it is a form of a halide. During this process of fixation, okay, this is called fixation. That means your light is falling on this chemical substance silver halide and it is sort of interacting with it. And now the light that is falling on this silver halide, it is a undulating light, or it has a certain intensity pattern, and depending on that intensity pattern, your silver halide will become silver or remain as silver halide. So, where there is light, it will become silver. Where there is no light, silver halide will remain as silver halide. So, this part is called fixation, basically a way of recording your pattern. Okay. The plate consists of metallic silver which forms dark spots on the plate. If gamma characterizes the photographic material, then after development the transmission factor of the plate is of the form tau is equal to E star E raised to minus gamma by 2. Okay, this part okay, you have to assume obviously. This is the transmission of that holographic plate, and remember we have taken a glass plate. We have taken a glass plate or a rigid surface because when the light is falling on this rigid surface, the phase is recorded very accurately, or if it is a moving thing like a thin film which is moving, then the phase changes, you know. So, we do not want that phase to change because that itself is a crucial data that we are locking into this interference pattern. And remember, if this is moving, that means the path difference of the light is changing, and if the path difference changes, then the phase also changes, okay, in recording any interference pattern or recording any superposition of waves. So, gamma is a characteristic of that silver halide of the plate. Okay. So, whoever is an expert on that will know exactly what it is. What we have to know is how we are recording on this hologram. Okay. So, the transmission factor is given by E star E raised to minus gamma by 2. So, gamma is the characteristic of the photographic material. So, we have to include it into our calculations. So, now this final E is equal to e to the power minus I omega t minus k z, like this, okay. And this whole thing, that is what we saw in the previous slide. Yes, something like this. Oh, so I have taken this part of the equation, this, see this part of the equation, okay, I have written there once again. That is sort of repeated here again. Okay. So, the transmission becomes this multiplied by this itself, or the complex conjugate of this E star E, okay, mod E square raised to minus gamma by 2. So, the transmission becomes again just doing a little bit of jugglery here and there, putting things left side and right side. Okay, and one more thing that you have to do know is, now E1 is much less than E0 under normal conditions. If you remember, E0 was the reference and E1 was the amplitude of the signal wave. Using the series expansion around 1 plus psi, 1 plus epsilon, where epsilon is small. Okay, here E1 by E0, if you do all this, you know, there will be somewhere where E1 by E0 comes. I am just using some of these mathematical terms so that we can get a nice little equation which can be interpreted well. So, I have used the series expansion of 1 plus epsilon raised to minus alpha by 2 is almost equal to this. Okay, so, I take just the first two terms. I have taken just these two terms and this is what I get here. Okay. So, I just do a little bit of algebra here using all this sort of mathematics here, and finally, I come to the transmission which is here. Okay, and I assume E1 is much less than E0. So, this number is very small, and plus 1 plus this. So, this number is very small and I can use this series expansion. Okay, so, what happens to the transmission? Tau is the transmission. So, I am still talking about the transmission. I have not said anything about the wave after it is transmitted through the hologram. This is all the transmission of the hologram. Okay. What would be the transmission? Because I have recorded with that light onto a plate, a rigid plate, and I have to know what is the transmission. Okay. So, the transmission works out to be this. Okay, simplifying it a little bit more, I can put this as a simplifying factor. Okay. This is a simplifying factor. This is finally my transmission. Now, but I am not interested only in the transmission. Now, I have to direct towards the hologram a plane wave along the path of the signal. Okay. So, my recording the hologram is over. Okay. I have done something, recorded something on this, but then I have this plate here. This is the signal. So, I have to put a reference wave. This was the reference wave, but in place of the signal wave, I have to put a similar kind of wavefront, a similar frequency, a similar a wave to reconstruct. Okay, so here I am. So, how do I, if I reconstruction, this is for the reconstructed part, is E2 e to the power minus, this is one more wave which is the same as the initial reference wave, but the amplitude is different. When I say the amplitude is different, E2, that means it is a different wave. The frequency remains the same, everything else is the same, but the amplitude is different. So, this is my reconstructing wave. Then what is the output of the hologram? That means I have a hologram here. This is my plate. I am putting in a new beam of light and I must know what is this output beam. This output beam is E out. Okay. That E out is something which I am talking about here. E out will be equal to reconstruction, the one that is coming in, and you have to modify it according to the transmission. So, I multiply it with transmission, not addition. When there are two waves superposing, you are doing an addition. But in this case, reconstruction, you have to just modify it with your transmission of this hologram. Okay. So, I put this reconstruction here into this was my transmission, here the transmission is here. Okay. So, I just multiply this by this, and then the E output turns out to be this big factor. There are 1, 2, 2 factors here. Okay. Just notice these 2 factors. Okay. So, here I show it in a wavefront. This is a wavefront. This is my hologram, which has that interference pattern recorded on it. This is symbolically showing the interference pattern. Now, what happens is this wave which is coming here just gets diffracted, some part of it gets diffracted, and there some part of it is just going ahead. So, you have one wavefront which is moving out this side, or one beam that is moving out this side, and there is one more beam or one more wavefront which is moving out this side. So, one is going at an angle and one is going there. So, basically, if you really think of it, this is something like a diffracted beam. So, this beam enters here and it sees these undulating lines, and because of that it gets diffracted out. Okay. So, I have these 2 factors. Okay. This one is almost like an amplitude. E2 is an amplitude, E0 also was one amplitude, E1 was one amplitude, and gamma is of course a constant of that material. So, this total part is the amplitude of this wave, and this wave is e to the power minus I omega t minus kz, which is actually this wave. It looks exactly like this wave, the reconstructing wave. Whatever I am inputting here, I am getting out as a transmission wave also. But there is one more factor. This part is all the amplitude, 2 gamma E0, E1, E2. This is all the amplitude, or say a constant. And then you have this wave, which is moving out at an angle theta. Okay, this itself gives you that this moves out at an angle theta. The wave vector is along this direction. Okay. So, the total phase is different here. Okay. So, this phase has sort of become the imitation, in a sense the imitation of this phase here. So, whatever phase was recorded on this is being in a coded way carried away by this wavefront. So, obviously, this wavefront has an information, this extra phase information, which was there in my original wavefront. So, this was a plane wavefront, this also becomes a plane wavefront, and this is also a plane wavefront. Okay, so, I get these 2 output wavefronts. But there is one more thing here. Sometimes you can write this as, instead of 2 gamma E0, E1, E2, e to the power all this, you can write it as plus one more term. Okay, so, there will be 3 terms. I have written it out here. You can always separate it out into the 3 terms here. Instead of 2, it is 1 plus 1. Okay. So, that is what I have written here. Quite often it is written that way, and one wave is a complex conjugate of the other. You just notice the phase term here, e to the power omega t minus kz, it is moving around the z axis. Then you have this additional phase of kx sine theta, which shows that it is moving out in, say, in this direction, and then minus this whole thing. this has a plus kx sin theta. So, these two are moving out in two different directions, one along the positive x direction and one along the negative x direction. So, basically you have three waves. This is the original, this wave which is going through the hologram and it is just coming through, and you have two additional waves and they are plane waves. Okay, so, here I had shown two because I had written it this way, but in actual fact, you know, when you take E star E, we are taking the complex conjugate and multiplying instead of just mod E square. So, this term can be separated out into this term. So, basically from the hologram, after there is a reference wave which has come in here, I get three terms. Okay. The light field has three plane waves. The first term describes a plane wave propagating in the positive z direction. The second term describes a wave propagating at an angle theta to the z axis. Okay, this is at an angle theta to the z axis and inclined towards the positive direction of x axis. The third term describes a wave propagating at an angle theta to the z axis, inclined toward the negative direction of the z axis. This light field represents the diffraction of a plane wave incident on a hologram. So, what have I done till now? I have recorded a hologram, and I have reconstructed okay. I have reconstructed that, I won't say hologram, reconstructed the original wavefront. So, my original wavefront, the signal wave, was a plane wave, and the reconstructed one is also a plane wave. I have reconstructed exactly that, and quite often, you know, this is called the virtual image and this is called the real image. Okay. Most of the time we are looking at this, but you will understand that a little bit more when I tell you how to reconstruct the image of a small point source. Okay. Here in the plane wave, it's just to understand how the waves can be represented mathematically and described on a physical way. And it is like a two-dimensional thing, you know, because the photographic plate is on the xy plane. And you can use Cartesian coordinates, which I have used here. Okay. So, now let us go to the hologram of a point object. So, now I'll try to construct what happens from a point object. We've seen a plane wave. Now, we have to construct a hologram of a point object. Now, the reference wave here is ER is E0 e to the power minus omega t minus kz minus kx sin theta. The theta is the same as that. See here, the theta, remember, was somewhere here. Okay. This is what we had before. The same prism, I have the prism here, and I have a plane wavefront. One part of it is shifted out through the prism at an angle theta, which becomes the reference wave. And this I have described before. The reference wave is given by this, which has an amplitude of E0, just like before. And then the phase term is given by this, and phase term is modified. The k is modified a little bit more, because k, the wave vector, has a component along this axis, which is this. Okay. So, here I have this. So, this is my reference wave. Now, the spherical wave from the point source is given by spherical. So, instead of calling it the signal wave, I am calling it the spherical wave. Basically, the spherical wave is the signal wave itself, but it is spherical because I have taken a spherical wave. So, suppose I have this is not my hologram, this is my holographic recording plate. This is just a point, a slit where the plane wavefront is coming here, and then it converts from this point, exactly at this point, it is converting into a curved wave like this. Okay. So, my reference wave is a plane wavefront, and my signal wave, which I call the spherical wave, is a spherical wavefront. Okay. It is coming out from a point, any point object. So, my object now is this point here at that slit. So, I must know what is the interference between these two. What is the interference between these two and what is getting recorded on this? I must know that. Okay. So, and then I can decide what kind of a picture will this give. The spherical wave is analogous to E signal, as I have said before. The spherical wave is represented through the exponential term I k x square by 2 z0. The total electric, yes. So, this is a new term. This is a new term because it is a spherical wave. This term itself shows that it is a plane wave, and this term with a quadratic x, with a quadratic term in it, this comes very often in case of Gaussian beams, where actually these wavefronts which are spherical in nature and they are growing outwards. Okay. They have to and they are phase fronts, that means each point on that wavefront has an equal phase. Okay. So, what this shows is I have a linear term, I have a phase change which is happening because it is travelling along this, but at the same time I have this quadratic term which represents this spherical wave. 2 z0, not 2, z0 is actually the radius of curvature of this wavefront. Okay. You will come across this very often in case of Gaussian beam profile. Remember the lecture where I had given the Gaussian beam profile. It had a radius of curvature which was given as Rz. Here I am calling it as Z0. Okay. So, there is a radius of curvature, and this radius of curvature remains the same, but the phase fronts keep changing. So, each time you have to include that factor in order to describe the movement of this wave along this. So, this comes very often in case of a Gaussian beam or diffraction effects, Fresnel effects, or Huygens principle if you are using. In all these cases you have to include these terms. All of them have this spherical kind of wave attached to it. So, that is why I have to put in this new term. Okay. So, we will see what is the interference pattern of this in the next lecture.